The Stanford Linear Accelerator was built to probe the proton with electrons, like Rutherford probed the atom with alpha particles. They both used scattering techniques. These techniques are key to understanding how the Higgs particle was found at CERN in 2012. So we'll take a little time to understand what they found and the principles involved. There are two basic types of scattering. One is called inelastic scattering, where both of the colliding objects change. For example, here we have some of one object's mass transferred to the other at the point of collision. The transfer absorbs energy, so conservation of energy doesn't hold. The other is called elastic scattering, where no parts of the participating objects are changed. Total kinetic energies are preserved, or nearly preserved. In both elastic and inelastic collisions, the conservation of momentum always holds true. Rutherford was examining alpha particle scattering angles off a gold atom target to determine the size of the nucleus. He had to use an alpha particle probe with fixed energy at 7.7 million electron volts. The Coulomb force was repulsive, and his target nucleus was fixed in the solid gold foil. So the target recoil velocity was tiny because the entire foil had to move. The SLAC experiment could vary the incoming electron energy up to 17 giga-electron volts. The Coulomb force was attractive, with significant target recoil when a high-velocity electron collided with a target proton. The SLAC experiment was designed to examine this transfer of momentum from the electron to the proton at various electron energies and scattering angles to find out if the proton's positive charge was distributed evenly throughout its volume. The physicists controlled the incoming electron's energy and momentum and carefully measured the outgoing energy and momentum for a particular scattering angle. With that, they calculated the amount of momentum lost by the electron. Given the conservation of momentum, the electron's loss would be equal to the proton's gain. Suppose we're counting 10-degree deflections as a hit. A relatively slow-moving, low-energy electron can get a 10-degree deflection far from the center of the proton. This would make the size of the proton look large. In addition, the interaction between the electron and the proton would be weak. We'd find that only a small amount of momentum would be transferred. If we increased the velocity of the electron and kept its distance from the proton the same, it would not be deflected 10 degrees, and the interaction would be considered a miss. An electron with this increased energy would have to approach closer to the proton to get deflected 10 degrees. This would have the effect of making the proton look smaller, and in addition, the momentum transfer would be greater. This gives rise to the concept of cross-section. If we take a look at the total area we are shooting into, and the smaller area that represents the target, we see that the probability of a hit is equal to the target size divided by the total area. You can see that as the target cross-section shrinks, the probability of a hit goes down. Of course, we have a large number of targets in the area, the liquid hydrogen protons, so we add them together to get the total cross-section. SLAC calculated the cross-section by controlling the number of incident electrons and counting the hits. Here's a graph of the interaction probabilities against the momentum transfer found by the SLAC experiment for electrons with energies below 7 giga-electron volts that scattered by 10 degrees. The closer to the target we get, the smaller the cross-section, decreasing the probability of a hit, while at the same time, the momentum transfer increases with each hit that we do get. The velocity of the electrons remained the same, indicating that no energy was being transferred to the proton. This is exactly what we would expect from elastic scattering. But at incoming electron energies between 7 and 17 gigaelectronvolts, this dependency changed significantly. In particular, for 3 final proton state energies, the momentum transfer dependence on cross-section was significantly weaker than for elastic scattering. And what's more, the protons absorbed significant amounts of energy from the colliding electrons. Physicists refer to this phenomena as resonance. To understand what's going on, we'll take a closer look at the final proton state. You may recall that Einstein's formula for mass and energy is E equals mc squared, but this only applies to a mass at rest. For a moving particle, the energy-mass conversion includes the particle's momentum. In our case, we see that the final mass of the proton goes up with an increase in energy and goes down with an increase in momentum. If you think of mass as confined energy, what is happening here is that the incoming electron's energy is being converted into increases in the mass of the proton. This is inelastic scattering, and the 3 resonances indicate the proton has 3 internal components.